All right, let's keep going. Pull out your notes, make sure you've got them, make sure you got your formula sheet out and a calculator with you, and yeah, get your writing shoes on. I'm going to try to move quick because you can pause the video. So your goal is to get through these notes. That's your homework for today. Okay, so we weren't quite finished this question because we hadn't done a squared plus b squared equals c squared to get this length. So just to refresh what we did, in red, we were adding up the vectors 3 meters west, that's this one here, and then we went 6 meters south, all the way down there, and then we went 4 meters, 32 degrees east of north, which means we went north, we went 32 degrees east, and that was a 4 meter displacement. Now this made it a lot more complicated, so I want to highlight what we did. We quickly determined that this x value, because we don't like angled things, so we wanted to get rid of the 4, right? And we replaced the 4 with its two what we call components, all right? Components are breaking it down into like the x values and the y values. And so the x value we found first was 2.1 meters. 2.1 meters. And that helped us to determine this green value here, that this must be 0.9, right? Because we were wondering, how far are we from where we started? Okay, we started here. This is our start. This is why the arrows are so important, right? Because otherwise, maybe we started here and went like this. No, we started here and we ended at this point, at the end of the vectors, right? So we went 3, 6, 4. We ended here. Now, how far are we from where we started? Well, we're definitely 0.9 meters to the west, right? Because we went 3, then down. It didn't really affect our east and west. And then we went 2.1 back. So we ended up 0.9 meters from where we started. But we also went down. And so we figured out our y1 value. That's the y value of this triangle as 3.4 meters, which means that if we had gone down 6 and then here we went up another 3.4, we ended up this value being 2.6 meters from where we started. And so if we're going to, what I'm going to do now is I'm going to take this stuff and I'm going to redraw it because that's our final answer. So we know that we went 0.9 meters towards the west. This is where we started, towards the west. And we also went 2.6 meters down. So I'm going to try to draw this nicely right about there. There we go. That's good. 2.6 meters down. And we are wondering, how far did we actually go? Where are we? The other thing we need to know is, what angle did we go at in order to get there? This is what we call our displacement. So we're adding up all these vectors to perfectly describe where we actually went. So if you wanted to just say, avoid walking this whole path, this is how I like to think about it. We're going to avoid walking this whole path, and we're just going to go straight there, right? Someone totally got lost, but we're just going straight there, beat them there. And so how do we find this? We start off here. Let's do this in green. What should we call it? Let's call it X. No, X is a bad letter. Let's call it R for the resultant. Okay, R. We can put any letter there. R squared equals 0.9 squared plus 2.6 squared. Now, why are we doing this? It's because a squared plus b squared equals c squared. So I'm treating r squared like the c squared, right? So this r squared equals a squared plus b squared. 0.9 squared and 2.6 squared. All right, so if we do this, then we get that r squared equals 0.9 squared plus 2.6 squared. That's 7.57, which means that r equals the square root of 7 point happened. 7.57. There we go. Right, we have to get the square root to get rid of that. And then we get that being 2.75, 136, dot, dot, dot. Oh my goodness. Equals, right, 2.75, 136, dot, dot, dot. And this round, remember, we're doing sig figs, and we should have two sig figs. This should be 0.90. Oh no. Let's do That's pretty brutal. This is looking like one sig fig here. And so let's just do 2. If you don't like it, relax. All right, 2.8 meters, right? I like to punch it all in and keep the number of sig figs I want, and we're going to keep 2 because let's just say, I don't know, I'm not liking this. We started with 2. Everything here at 2, so I'll be happy with 2. We should keep 2 sig figs. 2.8 meters is how far this is, okay? But we also need to know the angle. How are we going to find the angle? Well, what do we know here? We know the adjacent and the opposite side. And so what are we going to use? Adjacent, opposite, SOHCAHTOA. OA is what we're using. And so we're going to do tan of theta equals the opposite, which is the 2.6, over the adjacent, which is 0.9. And that gives us, that means that theta equals tan to the -1 of 2.6 over 0.9. That's what I punch into my calculator, and we get a final value for theta of second tan 2.6 over 0.9. We get 70.9 equals 71 degrees. So my final answer is, the resultant vector is 2.8 meters, angle of 71 degrees. Now we got to think of the angle. This is south of west. So you can see that, and there's our final answer. Nice. All right. Now that said, we got to move to the next question. There's one other way of doing this. Now you can see this was a bit of a pain, lots of work. We had to first break into components, and once we had broken into components, our 2 x values, then we had to subtract, or sorry, x and y value, then we subtract the y values and get our total y displacement, then we get our x total displacement, and then we made a new triangle, the resultant, right? That we call this the resultant triangle of all our work, and then we found the hypotenuse and the angle to get our final answer. And that's what we got to do, and it's super accurate. Now here's a less accurate way that you could do, and this is just to help you appreciate what we're doing. So we need a protractor, so I'll get a protractor. Let's see if this works. I got to show you how to use a protractor. Doesn't look good. Come on. There we go. Let's see if this works. Here, there. Awesome. Look at that. You guys need to use a protractor. Okay, and you also need a ruler. And so what we're going to do is we're going to, but you can use this here. So I'm going to say that each cell is 50. Okay. Each cell represents 50, 50 or 25. Let's try 25. 25 meters. Cool. Each cell represents 25 meters. And so what that means is we got to draw a bunch of lines. And so here's how you use a protractor. We got to start off by, well, we're adding just 2 vectors. And it's 200 meters north and then 300 meters, 30 degrees north of east. Okay, so let's pick a starting point. We're going to go north and then north again. And we're going to go also east. So I'm going to start down here. Right there. That's our starting point. Okay. And then I'm going to go 200 meters north. So I want a straight line. So I'm going to get my shape. You should get a ruler. I'm going to go straight north. Remember, they're 25. Let's say 25. So I'm going to go 50, 100, 150, 200. There we go. 200 meters. And you can write that in here even. 200 meters. And I'll rotate this. Whatever, that's good. All right, so I got that. And now I've got to draw 300 meters, 30 degrees north of east. Yikes. The way we got to do that is we line this up. Yikes, that's brutal. I'm losing control. Let's do this. Make this a lot smaller. There we go. Zoom in a bit. Okay, we got to get 30 degrees north of east, which means from east, it's 30 degrees. So what you do is line this up there. So do you see how I'm lining up that center dot with the edge of where I want to start? I would like to take this chance to announce today's winner. Okay, so once you've got it lined up, then make sure this 180, so it's lined up on this line. So this line right here is going straight through and it's totally lined up. So it's got to be totally flat. That's why you've got this grid here, okay? It's got to be totally flat. Your line is here, and now we've got to go 30 degrees north of east. So we start east and we go 30 degrees north of it. So I'm going to grab my shape and I'm going to start. Well, actually, what I'm going to do is I'm going to actually show you how to do it. Is we find this 30, so it's here right at 150, and we make it mark right at the edge of it, right there. Okay, that's where we want our line to go. Our line to go through that dot. And so now we've made our dot, and that dot represents 30 degrees. And so how do we fill it in? We get a shape, and we put a ruler here, and our line needs to go through. And now what you need to do is measure this out so that according to your scale, this is exactly 300 meters. Okay, so if this was 200 meters, 300 meters, it has to be like that's what this has to be, right? And so make sure that it is the right length. I can't do that nice in here. I don't have a ruler, but the big thing is make sure it goes over that dot and make sure it's exactly 300. So if this was like 20 centimeters, this would have to be 30 centimeters, right? So make sure it totally works. I think mine's a bit long. I should use a ruler, but I'm not going to because I'm doing this on Cami. I could do the same thing I got here and use a ruler, but forget it. Okay, so you should use a ruler. Make sure this represents 300 meters. Okay, and it's got to be perfect. You have to be perfect within a tenth of a millimeter. Remember, that's how accurate rulers are, within a tenth of a millimeter, plus or minus 3/10 or something. Okay, and so this represents, let's make sure we got arrows on here. So we went from there to there, and then we went from here to there, and now we've added those two vectors. Okay, but our resultant vector is the line that goes from the beginning to the end. So from here till there. And so if we did our scale properly, you should get a really nice triangle. All right. And just from mine, I don't think this is right. But as you saw here, if I'd measure now, I could use this and see that when I line it up, that the resultant vector would be 53.5 degrees. And its length, as I would measure, would be, it goes up, that was 8, 9, 10, 11, 12, 13, 14. It goes up 14 cells and over this. And so you can measure it with your ruler. Just line up your ruler and you see how far it is. And then you do the correct conversions to figure out a distance. So maybe that would be like, I don't know. I really should just get a ruler, hey? I'll pause this. Okay, I have got a ruler and I can't do it. I can't rotate the ruler. It's way better doing this by hand. So you'd want to rotate the ruler and measure exactly how long this line is and just write down that length, but convert it. So good luck. Finish this. Show it to me when you get it. See what you get. All right, that'd be super cool. Hope it rocks. I hope you get a really good, accurate thing. Okay, so what we're going to finish with. So finish that. Hopefully, I want you to actually do this by hand. And that'll help you appreciate doing it not by hand. Okay, let's finish off here. Just a few questions using acceleration from last year. This should be review. A bird is soaring down to the ground with a constant vertical descent 12 meters per second. Down. How far will the bird drop in 7 seconds? So here we've got a constant velocity and a time. So I like to always list my knowns. Remember, we're guessing. Use guess. So we're given velocity equals 12 meters per second. Down. We also know the time that it's falling is 7.0 seconds. And so what we're going to use is v equals d over t. And if we reformulate that, we're going to get d equals vt, right, multiplied by t. And that's if we reorient the formula. And so using that, we got d equals 12 times 7. And that gives us 84 meters. In the direction, down. Why not get the direction? Okay, so there's our answer. Cheetah goes up to its top velocity of 32 meters per second in 3.8 seconds. What's its acceleration? Okay, we're assuming it starts from 0, which means the delta change in velocity is 32 meters per second. That's how much it changed, right? It went from 0 to 32 in a time of 3.8 seconds. And so we're going to use the formula A equals delta V over T. And we don't need to modify it because we want acceleration. So acceleration equals 32 over 3.8. And that gives us a total of 8.4. And acceleration should be in meters per second squared. And it should have a direction because it's a vector. And so it should be also north because it's sped up towards the north. Very good. Meters per second squared are the units for acceleration. So we did this in grade 10. Hopefully you're remembering that. Let's try question 3. Try the question. Pause the video, try the question, and then see if you got it right. A diving golden eagle travels 187 meters down, 2.8 seconds. All right, so what are we given? We're given a displacement of 187 meters down. We're also given a time. Time equals 2.8 seconds. And we want to find the velocity. So we're going to use v equals d over t. And we don't have to reformulate that because that's what it is. And so we do v equals 187 divided by 2.8. And we get an answer of 187 over 2.8, 66.78. Sig figs gives us 67 meters per second with a direction down. It then slows to a stop. So here's its velocity. It slows to a stop at a rate of 8.3 meters per second squared. How long does it take for the eagle to stop? Okay, well, we know the change in velocity is from 67 to 0, the change 67 meters per second. We know the acceleration is 8.3 meters per second squared. And we want to know the time. And so what we're going to do, we're going to do this. A equals delta V over T. But we're going to reformulate that because we want to solve for time. So we swap time and acceleration, right? We can swap these two because we want T over there. And T's on the bottom, so we get T equals delta V over A. It's kind of nice. So we can reformulate the equation. And so if we do it that way, we got T equals delta V is 67 over A, which was 8.3. We get an answer of 67 over 8.3. 8.07. Whoa, let's do sig figs. 8.1 seconds is the unit that we're using because it's meters per second squared, and seconds is our time unit. So there's a few examples. There's scribblings from our Kahoot. There's a few examples. So your homework was to finish these notes. There's going to be some homework tomorrow at class. Tomorrow during class, I want you to show me this completed, and then I'll give you some questions to work on.